Alright, just giving the stream a little bit of time to warm up. Okay, we should be good. Cool, so yeah, continuing from where I had left off last time, basically, I want to turn my music down a little bit. Sorry. Alright, cool. So yeah, this is where I left off last time. So I had a histogram, right, plotted of the time spent in each capacity percentile. So the time spent in each sort of bucket of capacity for the station that I've been looking at, this Greek Street station. And so to continue with this analysis, I thought it'd be interesting to look at what times of the day is the station actually within, the certain capacity percentile. So that is what I think I will want to work on today, and I'll just be continuing with the same script again, just going to do a little bit of brainstorming of what I want to do. So basically, I was able to count the number of instances here when the station was within a certain percentile range. I think what I want to do now, well, I need to figure out, right, so I want to say given a certain percentile range, right, count the time spent in that percentile range, or count the occurrences spent in that percentile range as a function of hour of day. Which is basically to say that I want a histogram of each of these buckets as a function of time. So I'll take the 0% bucket, for example, which is the one that this station spends the most time in, and figure out what percentage, what time during the day is the station at 0%, right, and how that time is distributed. Or how that probability is distributed, I should say. Right, so what I can do is, again, I'll just do a test case, because I will eventually want to do this for all of these buckets and all the hours of the day, but right now I'll just do a test case of just one capacity bucket and 1 hour of the day. So I'll say I want, basically, what do I want? Well, first I'll say what range I want. So I'll say percentile range equals, should I say range? I'll just say range for now. I'll make it 0, right? And then I'll say, let's see, I want to find all the instances when capacity versus time is at 0, right? And so that's easy enough, because I can really just copy paste this code, which was doing this boolean. Ah, that's right, okay, I'm kind of remembering now. It's been a little bit since the last stream, so I've forgotten what I was using for all these variables. But, right, percentile range is actually the plus minus range of what I want to look at in terms of the bucket size. So let's just make it, you know what, I can just reuse the one from before. I'm not going to change it. Right, that's perfectly fine. Instead, what I want to care about is center percentile. I said that's 0. Right, and now what I can do is I can find all the occurrences of capacity over time when it is within this percentile range, centered around 0. So I'm going to call this, I usually like to call this index index in percentile range equals, oh my god, equals that array, right? Good. And then what I can do is I can grab all the timestamps that are within that array. In range hour vec. Or, even better, I can just directly grab the hours. So hour vec equals to, oops, sorry. Let's say hour vec in range, which is already a variable. I'm not sure what for. I have forgotten at this point. Let's see, where was it using for? Okay, I see. Right, I'm actually doing something similar again. So here I was grabbing all the hours within, I think all certain hour and day range. Yeah, okay. But here I'm looking for all the hours, all the x-axis data, where the y-axis data is within this percentile range of capacity. So hour vec, let's say in percent rate, in the percentile range equals hour vec, and then index with this Boolean vector. And then I want to say, that, think a little bit. Yeah, okay, so now let's pick, for example, I want to count how many instances of hour vec is within the hours of, say, 8 or 9 a.m., right? And basically, I can use this code again. Let's say I just print this. The number of times that this vector exists at, let's say, 8 o'clock. Or, sorry, greater than or equal to 8 o'clock. And less than or equal to 9 o'clock. I don't know if the parentheses are needed, but better to be safe. Okay, let's have a look at that. Close that. And right, plotting things should be at the very end. Uh-huh. 107. Okay. We got a number, so something happened, and I think that's good. I'm not sure. Is there some way to verify? There's probably some way to verify this number, but I'm just going to kind of trust that it is the right number. Yeah, so now let's put together a histogram. Right. Oh, there's one way to verify, but I'll have to load all the other hours first, actually, and then compare the sum. So, okay, so we'll go ahead and do this for every hour, and I'm pretty sure I should be able to do this in a list comprehension, and I kind of like that because it would be very Pythonic and condensed. So it would be num, or how about this? Count in percentile per hour equals, make a list, right? and it'll be np.count non-zero, so this code, that is the function of hour percentile in percentile range greater than or equal to the starting hour inclusive and less than or equal to the ending hour exclusive. Right. This is going to be a really long piece of code, line of code, so I'm actually going to try and break it up if I can. New lines, I use slashes in Python. Try to line everything up. It's nice and legible. Alright, np count non-zero for I hour in range 24 hours. Alright. And we can plot that data. Figure plot. Make another histogram. In this case, the x-axis will be hours of the day. So, right there, range 24. And then the y-axis will be the counts. And the width, well, each hour is 1 hour long, but maybe I make it 0.8. That should be, maybe that would make it a little easier to read. And then we'll title this, okay, so histogram of time, and this is actually kind of the wrong word to use. This should actually be, let's see, histogram of, what to say, data counts, timestamps, spent, yeah, let's say timestamps. And then this one also, histogram of timestamps. This is timestamps per hour spent at 0 capacity. So that's what we're looking at. And the X label will be hours, or hour of the day. And the Y label will be, we'll just call it counts. And let's give that a go and see how that looks. Aha, okay. Good. Yeah, good. I think that's very revealing. So basically, right, what we see is something that does kind of look like a normal distribution, and it's you know, clearly centered somewhere in the middle of the day, let's say noon, right? Really between like 10 a.m. and let's say, I don't know, this is where it kind of falls off again, so 3, 4, 5 p.m., right? Between the hours of 10 and 5 p.m. are when you're most likely to find that the station is just totally empty, right? And these are the number of occurrences when we found in this data that this station was totally empty. And that makes perfect sense to me, because that's the way the work week goes, right? In the morning, people check out all the bikes, leaving the station empty, and then in the afternoon, people return them, filling up the station again. Yeah, so we could do this for all of the different capacity percentiles, but that would be a lot of data, and I think that's maybe too much data to show. So what we could do is we could look at a specific selection, like a sampling of the different capacities, right? So I mean, of course, looking at 0 is useful. Looking at 1 might be useful, although the counts are really low. So that data is not really, you're not going to have a large sample set there. And I mean, we already know it's almost not going to spend any time at 100%. So maybe something like 0, and then somewhere kind of in the closer to the middle, maybe like 40%-ish. And then something in the higher end, like 70%. we can have a look at those. So what would be nice would be to make this some way to make this so I'm not like repeating code, because I don't like to repeat code, and that is just bad practice anyways. Let's say center percentiles. So I should be able to just modify this code actually. Let's say center percentiles that I'm looking at here are 0. We'll say 40%. 40%, what multiple of 1 over 15 gives you 40%? 40% is 4 over 10. I think I'm just going to crunch the numbers. So 40% is of course 0.4. 0.4 divided by 1 over 15 will tell me how many? 6. Okay. Oh, that was easy. So now we have 6 over 15, and I think this might have to be a float. And then 70%, or actually we could do 80% because that'll just be another perfect multiple, so 12 over 15. Cool. Okay. And then I want to run this code here for each of those values. So I'll make that for loop. But then the variable that gets saved to, I'll have to modify. So for, I don't know what to call it, CP in center percentiles. For each selected percentile range, we will get the I need this, right? I think I do. Yeah. Get the occurrences when the station is in that percentile range. Right, that's this vector. Oops, what just happened? And then this one is getting the hours for each of those occurrences, and then finally counting the occurrences per hour. And what I need to do is figure out how to turn this variable into a 2D vector, which is what I want. I think it shouldn't be too hard, but I want to pre-allocate it. So I'll say counts in percentile, counts, let's say counts per hour per percentile equals numpy dot, should I make it empty? I guess I'll make it empty, and I will look up the syntax again for this, numpy empty, to know how to allocate a 2D vector or a matrix. Shape int or tuple of int. Okay, so make it a tuple, right? Shape will be. We'll make it, well, since I said per hour and then per percentile, right? First, the first dimension will be hour, so I'll say, well, we know there's 24, so it'll be 24. That's easy enough. And then per percentile is length of this list. And that should do it, right? And then all I have to do here is assign, and hopefully this works. I'm not sure if this assigning works. I'll assign, is this all? I think this is all of those values, and this, okay, CP and send. I also want an index. So actually, let me say for I percentile in range length center percentiles, right? For each of those, get the occurrences, which is actually, this needs to be center percentiles, I percentile here as well. So that's getting the right percentile value to look for. And then you get the hours for each of these occurrences. Okay, and then you count the occurrences per hour, which is taking this first row, or sorry, all the rows, this column equals all this stuff that we had before. Nothing that has to change. Let's make a note where this for loop ends. And for I percentile, blah, blah, blah. And let's plot. Okay, if this worked, I will be able to plot as I did before, but I do this 2D indexing. All right, I'll just try it out. Uh-oh. So plot's open. Yep, cool. It worked. It worked. Well, it worked for that specific case, but let's see if it worked for the 40% case. Okay, yeah, it did. Okay. Well, I mean, it gave us a different plot, so something happened. And then let's look at the 80 percentile case. And then I will script it all up to plot all three of those plots together. It would be nice to plot them side by side, so I'll try to figure out how to do that. In MATLAB, you would use something called a subplot to plot things side by side. This in NumPy, well, hopefully there's a similar function. Let's see. But yeah, okay. Of course, that title is, wrong, but all right, let's do this. So, sorry, not NumPy, matplotlib subplots. Okay, we do indeed have subplots. Matplotlib, okay, pyplot subplots. So you specify the number of rows, columns, and then stuff. Create a figure and a set of subplots. This utility wrapper makes it convenient to create common layouts of subplots, including the enclosing figure object in a single call. Alright, and then is there an example of how I can use this? Here we go. First, create some toy data. Alright, so you got some sinusoid. Create just a figure and only one subplot. Fig ax equals plot.subplots. Ax.plot, so you plot this data, okay. And then create two subplots and unpack the output array immediately. What does that mean? F, ax1, ax2, ax1 plot, ax2 scatter. Create four polar axes and access them through the returned array. Weird. I don't know what that means, but okay. Share an x-axis with each column of subplots and blah blah blah. Same as. Alright, let's give this a try. I'm just going to copy and paste this code, see if I can reuse it. So, I'm going to comment that out. And use subplots to plot our count data. So F will be the figure, x1 and x2 are two axes. What would be interesting actually is to see what this does to begin with. So I'll do that. Try out their example. Okay. I don't know why that says sharing y-axis. Sharing y-axis. I do want to share a y-axis. I don't know what here specifies that they share the same y-axis, but it would be nice. Oh, I see, right here. Share y equals true. Oh, interesting. Okay, that'd be nice. That'd be interesting to see because you'll not only get to see the distribution between these different histograms, but you'll also get to see the relative total number of counts between these different buckets, which you'll see fall off. So I really want 3 plots side by side. That means we'll have 3 axis handles being returned, and then we know exactly what we want to plot, right? The first one is a bar plot right here of our hourly count data, and then I can set the title. I see. Okay, this is histogram at or let's say counts per hour at 0 capacity, and then I can just copy this 2 more times and plot the rest of the data, which is this is 1 and this is 2, and you know what, I can actually, I'm pretty sure this is 0.4, but I can actually display what this is by using string concatenation. I don't know what to call it. Center percentiles 1 capacity, and you know what, I'll just say, I'll shorten this and just say that, and then I'll say center percentiles 2. Alright, let's give that a go. See how this looks. Uh-oh. Unsupported operand type. Ah, right. I believe I have to wrap these with a data type. Okay. Oh, fun. That's fun. That is actually, I did not know you could do that. Huh. Oh, you can plot bars on top of each other. Oh shit. Maybe that's what I want to do actually. I was thinking to compare them side by side, but maybe on top of each other is more useful. But yeah, I was mixing up the axes. Cool, there we go. How about this? How about I just say 0 capacity here? And it does look like, yes, I am calculating the right capacities. 0, 0.4, 0.8. There we are. Yep. Cool. Yeah, so this is good. Very good data to look at. So basically this tells us that you'll find this station more often than not. It's going to be empty in the middle of the day after all the bikes have been checked out. And then there's kind of an even probability that you're going to have what I would call like a healthy capacity, which is between 0.4 and 0.6, right? Basically, you have an even chance of finding the dock that way across the day. But, you know, that likelihood is lower, right? Because there's just less counts overall when compared to the zero capacity case. And then you are also, you can see from this histogram of the case where you're at almost full capacity, that this case simply just doesn't really even occur with much probability. But when it does, it's kind of almost an equal probability that you'll find it, the dock at that higher end of capacity. So yeah, I think this is very informative and very useful to look at. I see my timer's about to expire, so this is where I will call it for tonight, and we'll continue from here next time. Cool. All right, ending the stream. Thanks to anybody who's watching. Have a good one.